candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. The Earth is a rocky planet that orbits the Sun in a nearly circular orbit. It rotates from west to east on its axis, which is a line through the north and south poles. The axis is tilted at an angle of approximately 23.4 degrees from the vertical. The Earth completes one full revolution in approximately 24 hours, or 1 day. This rotation creates the apparent daily motion of the Sun rising in the east and setting in the west. This rotation cycle is responsible for the day-night cycle we experience. Day and night. Day and night are caused by the Earth's rotation on its axis. The side of Earth facing the Sun experiences day, while the opposite side experiences night. Rising and setting of the Sun. This rotation also makes the Sun appear to move across the sky from east to west. During the equinoxes, day and night are roughly equal in length, and the Sun rises due east and sets due west. However, the Sun's exact rising and setting points change throughout the seasons. In the northern hemisphere, above the equator. In summer, the Sun rises north of east and sets north of west. Midday brings its highest point in the sky, and daylight hours reach their peak around June 21st, the summer solstice. In winter, the Sun rises south of east and sets south of west. It reaches its lowest point in the sky at midday around December 21st, the winter solstice, when daylight hours are at their minimum. The Earth's orbit and its seasons. The Earth orbits the Sun once in approximately 365 days. This is 1 year. The combination of the orbiting of the Earth around the Sun and the Earth's tilt creates the seasons. Over parts B, C and D of the orbit, the northern hemisphere is tilted towards the Sun. This means daylight hours are more than hours of darkness. This is spring and summer. At C, this is the summer solstice. The northern hemisphere has the longest day, whilst the southern hemisphere has its shortest day. Over parts F, G and H of the orbit, the northern hemisphere is tilted away from the Sun. This means there are shorter days than night. This is autumn and winter. At G, this is the winter solstice. The northern hemisphere has its shortest day, whilst the southern hemisphere has its longest day. At A and D, these are the equinoxes. Night and day are equal in both hemispheres. The situations in both the northern and southern hemisphere are reversed. It is autumn and winter in the northern hemisphere, but at the same time it is spring and summer in the southern hemisphere. Moon and Earth. The Moon is a natural satellite of the Earth. It orbits the Earth in roughly a circular path once every 27.3 days. This takes about a month. The Moon rotates on its axis once in about 27.3 days, keeping the same side facing Earth. While we cannot see the far side directly, astronauts have orbited the Moon and spacecraft have photographed it. The Moon shines by reflecting sunlight, it does not generate its own light. Phases of the Moon. The different appearances of the Moon throughout the month, as seen from Earth, are called its phases. In the image, the inner circle correctly shows that half the Moon is illuminated by the Sun at all times. The outer circle shows how the Moon appears from Earth at different positions in its orbit. During the new Moon phase, the Moon is positioned between the Earth and the Sun. Therefore, the side facing Earth is not illuminated, making it invisible. This means the Moon is unlit as seen from Earth, so it is not visible. At the full Moon phase, the Earth is between the Moon and the Sun. Therefore, the side of the Moon facing Earth is fully illuminated by the Sun, making it appear completely lit. In between these phases, we see crescent shapes as the Moon is partially illuminated by sunlight. Orbital speed. When planets or moons orbit another object, their paths are often nearly circular. In one orbit, the object travels a distance equal to the circumference of its orbit. This distance is equal to 2 pi r, where r is the average radius of the orbit. Time is the one period is the time that it takes to complete one orbit. Therefore, the average orbital speed can be calculated by dividing the total distance traveled in one orbit by the orbital period. This relationship is expressed by the equation v equals 2 pi r over t, where v equals average orbital speed in meters per second. R equals average radius of the orbit in meters. T equals orbital period in seconds. The orbital period is the time it takes for the object to complete one full orbit. The orbital radius is always measured from the center of the object being orbited to the object doing the orbiting. For example, calculate the speed of a satellite that is orbiting 200 kilometers above the Earth's surface and complete one orbit in 1 hour 24 minutes. The radius of the Earth is 6,400 kilometers. The radius of the orbit is measured from the center of the Earth, so the radius of the Earth plus the height of the orbit above the Earth's surface. Radius of orbit equals 200 plus 6,400 is equal to 6,600 kilometers, or equals 6,600,000 meters. Orbital period equals 60 minutes plus 24 minutes times 60 seconds equals 5,040 seconds. Orbital speed equals 2 pi r over t. To substitute, r equals 6,600,000. T equals 5,040. Its result is 8,200 meters per second. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. The Solar System. There are many planetary systems in the universe, with planets orbiting a host star. Our planetary system is called Solar System, and it is located in an outer spiral arm of Milky Way galaxy. Our solar system consists of our star, the Sun, and everything bound to it by gravity. The Sun lies at the center of the solar system. It is a star that makes up over 99% of the mass of the solar system. The 8 planets in our solar system in ascending order of the distance from the Sun are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. There are 4 rocky and small planets, Mercury, Venus, Earth and Mars, that are nearest to the Sun. These are small and dense, and mainly made of rock and iron. There are 4 gaseous and large planets, Jupiter, Saturn, Uranus and Neptune, that are the furthest from the Sun. These are large, mainly gas, and have no solid surface, although they do have a solid core. The 8 planets travel the Sun in the same direction, and in approximately the same plane. The further a planet is from the Sun, the lower its average surface temperature. This is because the intensity of the Sun's radiation weakens with increasing distance. However, as shown in the table, Venus is an exception. Its average surface temperature is higher than Mercury's even though it is farther from the Sun. This is because Venus has a thick atmosphere rich in greenhouse gases, which trap heat and raise the temperature. There are an unknown number of dwarf planets which orbit the Sun, such as Pluto, Eris, Haumea, Makemake, Ceres and others. There are dozens of moons that orbit the planets as near-circular orbit. Moons are an example of natural satellites. There are artificial satellites, are man-made, and can orbit any object in space. There are millions of asteroids. It is a small rocky object that orbits the Sun. The asteroid belt lies between Mars and Jupiter. There are millions of comets that orbits the Sun as highly eccentric elliptical orbits that extend beyond the planets into the Kuiper belt. Comets are made of dust and ice and orbit the Sun in a different orbit to those of planets. The ice melts when the comet approaches the Sun and forms the comet's tail. There are millions of meteoroids that are rocky fragments of asteroids, comets, moon and planetary collisions. They are much smaller than asteroids, ranging in size from tiny grains up to a meters. Further from Neptune, we have discovered Kuiper belt and Oort cloud. Gravitational force. There is a gravitational attractive force between all objects with mass. The gravitational law of Newton states that the attractive force between two masses is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The greater the mass of each object, the stronger the gravitational attraction between them. The closer the objects are, the stronger the gravitational attraction between them. The further apart the objects are, the weaker the gravitational attraction. If the mass of one object is doubled, the forces between them are doubled. However, doubling the mass of both objects together, the forces between them increases fourfold. This is because the force is proportional to the product of their masses. If the distance between two objects is doubled, the forces between them are quartered. This is because the force is inversely proportional to the square of the distance. These forces obey Newton's third law of motion: every action has an equal and opposite reaction. This means that the gravitational forces between two objects are always equal in magnitude and opposite in direction, even though they act on different objects. Gravitational field strength. The gravitational field strength, at a specific point, is the gravitational force exerted per unit mass on an object placed at that point. It is measured in newtons per kilogram. It is a vector quantity, meaning it has both magnitude and direction. The direction is always towards the mass. The gravitational field strength is directly proportional to the mass of the object and inversely proportional to the square of the distance from the object's center of mass. The greater the mass of the object, the stronger its gravitational field. This is why Jupiter, with its massive size, has a much stronger gravitational field than Earth. As shown in the table, a clear relationship exists between the mass of a planet and its gravitational field strength. Heavier planets tend to have stronger gravitational fields. Earth's gravitational field strength is roughly 10 newtons per kilogram, while the Moon's is about 1.6 newtons per kilogram, 6 times weaker. The farther away you are from an object, the weaker its gravitational field. This is why the gravitational field strength decreases as you move further away from a planet's surface. Objects in orbit. With no force acting on any other object in the space, so they will travel through space in a straight line. Gravitational forces exist between all masses, providing the centripetal force that causes planets and other objects to orbit the Sun and moons to orbit planets. Moon and their orbits. Moons are natural satellites that orbit planets because they are closer to their planets than the Sun, experiencing a stronger gravitational pull. These orbits are often not perfectly circular, but they are generally elliptical with the planet at the center. Therefore, the orbit of moons are approximately circular, with the planets at the center. Planets and their orbits. The Sun contains most of the solar system's mass, causing its gravity to pull planets, comets, and asteroids into orbits around it. The Sun's gravitational field strength decreases with distance from the Sun. This causes the orbital speed of planets to decrease farther from the Sun, because the weaker gravitational attraction results in a lower centripetal force, requiring less speed to maintain the orbit. This also leads to longer orbital duration. These orbits are often not perfectly circular, but they are generally elliptical with the planet at the center. Therefore, the orbit of planets are approximately circular, with the Sun is at the center. Comets and their orbit. Comets have highly elliptical orbits, meaning they are elongated compared to planets that is nearly circular orbits. As a comet moves further from the Sun, its speed decreases due to the weakening gravitational pull. At this point, some of its kinetic energy converts into potential energy. As the comet approaches the Sun, the gravitational pull increases, causing the comet to speed up as it gains translational kinetic energy. This happens because some of its potential energy converts back into kinetic energy. The ice melts when the comet approaches the Sun and forms the comet's tail. The comet's tail is always directed away from Sun. At here, comet moves fastest, longest tail and most easily seen. At here, comet moves slowest, shortest tail. Accretion model of the solar system. The accretion model explains how our solar system developed over 4.6 billion years ago, also accounting for the differences in the types of planets we see today. Planets are thought to form along with their stars. Nebulae are clouds containing elements like helium, carbon, and oxygen, composed of interstellar hydrogen, dust, and gas. It is called interstellar clouds. Gravitational forces, or gravity, pull the interstellar clouds together. The cloud swirls into a flat, spinning disk with a dense blob in the center. Temperatures and pressures at its core trigger thermonuclear fusion, and the blob begins to shine as a star. In this disk, tiny dust particles bumped into each other and stuck together, like snowballs rolling downhill. Over time, these clumps grew bigger and bigger, eventually becoming planets. The closer a clump was to the hot Sun, the hotter it got. This meant only sturdier materials like metals could stay solid, forming small, rocky planets like Mercury, Venus, Earth and Mars. Farther from the Sun, it was cooler, allowing water, methane, and even light gases like hydrogen to freeze and join the party. This led to the formation of giant gas planets like Jupiter, Saturn, Uranus and Neptune. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Our Sun as a star. Our Sun is a medium-sized star composed primarily of hydrogen and helium. It radiates most of its energy in the infrared, visible and ultraviolet regions of the electromagnetic spectrum. Stars exist in a wide range of sizes and colors, from yellow stars like our Sun to red dwarfs and from blue giants to red supergiants. Color classification is used for stars, as the color they emit is related to their surface temperature. Red stars are the coolest, with temperatures around 3000 Kelvin. While blue stars are the hottest, with temperatures reaching around 30,000 Kelvin. Nuclear fusion in a star. In the center of a stable star, where immense pressure and temperature exist, hydrogen nuclei fuse to form helium. This nuclear fusion reaction can be represented by the following equation. Deuterium and tritium, both isotopes of hydrogen, can be fused to form a helium nucleus and a neutron. A huge amount of energy is released in this reaction. This energy exerts a pressure that prevents the star from collapsing under its own gravity. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. The Milky Way. Galaxies are made up of billions of stars. The universe is made up of many different galaxies. The Sun is one of billions of stars in a galaxy called the Milky Way. Other stars in the Milky Way galaxy are much further away from Earth than the Sun is. Some of these stars also have planets which orbit them. Astronomical distance. Stars are so far apart that astronomers use special units to measure their distances. An astronomical unit, AU, is the average distance between the Earth and the Sun. It is approximately 1.5 times 10 to the power of 8 kilometers. Light year. 1 light year is the distance that light travels in 1 year. It is approximately 9.5 times 10 to the power of 12 kilometers. The speed of light is approximately 300,000 kilometers per second. 1 year has 365 days. 1 day has 24 hours. 1 hour has 60 minutes. And 1 minute has 60 seconds. Using the formula distance equals speed multiplied by the time. 1 light year equals 300,000 times 365 times 24 times 60 times 60 is equal to 9.5 times 10 to the power of 12 kilometers. Star formation. A star is formed by the interstellar clouds of hydrogen gas and dust called a nebula. A protostar is an interstellar cloud collapsing, causing an increase in temperature as a result of its internal gravitational attraction. Nuclear fusion reactions occur within the core of a protostar. Hydrogen nuclei fuse to form helium nuclei, releasing heat energy and light energy, which keeps the core hot. A protostar becomes a stable star when the inward force of gravitational attraction is balanced by an outward force caused by the high temperature in the core of the star. This stable star is main sequence star. Most less massive stars expand to form red giants, and more massive stars expand to form red supergiants, when most of the hydrogen in the core of the star has been converted to helium. A red giant from a less massive star forms a planetary nebula with a white dwarf star at its core. A red supergiant from a more massive star explodes as a supernova, forming a nebula containing hydrogen and new heavier elements, leaving behind a neutron star, or a black hole at its center. The nebula from a supernova may form new with orbiting planets. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. The universe. The universe contains many billions of galaxies. The Milky Way is one of galaxies in the universe. Its diameter is approximately 100,000 light-years. There are 3 types of galaxies as spiral, elliptical and irregular. Our Milky Way is a spiral. Doppler effect. When a stationary ambulance car emits sound waves, the wave fronts spread out symmetrically, forming circles around the source. If the wave source moves, the waves can become compressed in front of it and stretched behind it. This movement changes the wavelength and frequency of the waves. In front of the source, the wavelength decreases and the frequency increases. Behind the source, the wavelength increases and the frequency decreases. This effect is known as the Doppler effect. The Doppler effect also affects light. If a light source moves away from an observer, the wavelength of light it emits increases. This is known as a redshift, because the light appears to shift towards the red end of the electromagnetic spectrum. Redshift. Redshift is an increase in the observed wavelength of electromagnetic radiation emitted from receding stars and galaxies. This means that the light reaching us from these objects has its wavelength stretched, shifting it towards the red end of the electromagnetic spectrum compared to the light we observe on Earth. This shows the electromagnetic spectrum from our Sun, or stationary source in laboratory. This shows the electromagnetic spectrum from a moving distant galaxy. This shows that the light from a distant galaxy shift towards the red end of the spectrum. By measuring the amount of redshift in the light from distant galaxies, astronomers can estimate their recession velocity and determine that the universe is indeed expanding. This finding supports the Big Bang theory, which proposes that the universe originated from a very hot, dense state and has been expanding ever since. Hubble's law. Edwin Hubble investigated the spectra of light emitted by numerous galaxies. The speed at which a galaxy is moving away from the Earth can be found from the change in wavelength of the galaxy's starlight due to redshift. He found that the further away a galaxy is, the greater its redshift, and so the faster it is moving away from us. The distance of a far galaxy is determined by the brightness of a supernova in that galaxy. As shown in the graph, the relationship between a galaxy's recession velocity and its distance from Earth is depicted by a straight line passing through the origin. This indicates that the speed of galaxies moving away from Earth is directly proportional to their distance, a principle known as Hubble's law. So, we can express this relationship as v equals h0 d, where v is the recession velocity in meters per second. D is the distance of the galaxy from Earth in meters. And h0 is Hubble's constant. It is determined by the graph's gradient. It is approximately 2.29 times 10 to the power minus 18 per second. From the graph, we see that more distant galaxies are moving away at a faster velocity. The galaxies closer to the Earth are moving away at a slower velocity. The gradient of graph is v over d, which is the Hubble's constant. The age of the universe. All distant objects show a red shift, and so they are all moving away from us. This implies that the universe as a whole is expanding. If we imagine time running backwards from the present, then the known universe would contract back to a point where everything is in the same place. This would be the time of the Big Bang, when everything first exploded outwards from that single point. Therefore, if we can find the Hubble's constant, it will tell us how quickly the universe is expanding. From this we can work out when it all started. For an object to travel a distance d, 0, from the beginning of time, at a speed of v, 0, the time taken t, 0, can be calculated from the basic equation for speed. If we consider the gradient of the Hubble graph, h, 0, equals v, 0, over d, 0. We can rewrite the time equation as substituting with the measured value of h, 0, as 2.29 times 10 to the power of minus 18. We get t, 0, equals 4.37 times 10 to the power of 17 second, which translates to approximately 14 billion years. This is the age of the universe. This age is an estimate due to the approximate value of the speed used in the calculation. Cosmic microwave background. The discovery of the cosmic microwave background radiation led to the Big Bang theory becoming the currently accepted model. The cosmic microwave background radiation was produced shortly after the universe was formed, and that this radiation has been expanded into the microwave region of electromagnetic spectrum as the universe expanded. The microwave radiation is observed at all points in space around us. The cosmic microwave background radiation is represented by the following map. The cosmic microwave background radiation map with areas of higher and lower temperature. Blue area represents the lower temperature. Orange-red area represents the higher temperature. Places with higher temperature have a higher concentration of galaxies, suns and planets. Places with cooler temperatures have a lower density of galaxies and stars. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.